This is part of the series of online presentation materials for the WRF modeling system. These presentations refer to version 4.2 of the modeling system. This particular talk is about Program Real, the description and general functions of that particular package. It's identified here in the middle with the .exe afterwards. The Real program accepts input data from WPS. It generates data that will be provided to the WRF model itself, WRF.exe. Overall, these presentations are grouped into a number of categories. There is an initial suggested grouping that should be taken in order: an overview, the two talks about general descriptions, and then the two talks about setup and run. This is the presentation of the description and general functions for the Real program. There is an assumption that the viewer has already seen the WPS description and general function, and following on to this talk, there will be setup and run presentations for both WPS and the WRF/Real system. This talk goes over what is actually done inside of the Real program. When we start talking about the function of the Real program, one of the things that we're going to have to do is include a lot of definitions so that we all are starting from the same place. From there, we're going to move on to what is required to actually run the Real program. So what are the standard input variables? We want to know what variables are optional, what variables are mandatory, where do they come from, and there are certain questions that we have about restrictions on the vertical coordinate from the data that comes from WPS from MetGrid. Inside of the Real program and inside of the WRF model, there is a base state that is computed and used. How that base state is defined, how it impacts the vertical coordinate, and the definition of the potential temperature variable will be discussed. When we run the Real program, in addition to data coming into the program, we have data that comes out of the program. We need to know what those files are and how we can look at those files and determine whether or not it was a successful Real run. Of course, the whole purpose of the Real program is to handle vertical interpolation. Just like the WPS MetGrid program handled all of the interpolation horizontally to the domain that the modeling system would like to have, the Real program does the vertical interpolation to the computational coordinate that the WRF model is going to be using. There are some suggestions that we have, and those recommendations are basically to be very careful. Finally, a small piece about vertical interpolation is also soil level interpolation. It's really an initialization for physics, and this is a good placeholder to tell us why and when we have to rerun the Real program if we're going to modify options inside the name list for the WRF model. There are two preprocessors for the WRF model, one for an idealized initialization and one for real data initialization. The one for idealization or ideal initializations is referred to as ideal.exe. When we're going to do real data simulations with the WRF model, we call the preprocessor that takes data from WPS and provides modified data and sends it into the WRF model. That's referred to as the Real program or real.exe. The real.exe program is available as both either a serial or a distributed memory parallel job. You don't really get very much performance benefit from running distributed memory unless you have a fairly large domain. But what you do get is an aggregate of a fairly large amount of memory if you run on multiple processors. The Real program is not computationally bound. The Real program is automatically generated whenever you try to build the WRF model. So it's kind of a program an executable of a program that you get for free. The real program, the WRF model, are entirely separate from WPS. The real program, the WRF model, have the same registry, they're in the same directory structure outside of WPS. The real program takes input data from WPS, vertically interpolates it, does a little bit of diagnostic / transformation, and it provides data that is suitable for input into the WRF model. We call it the real.exe or the real program because, as opposed to an idealized simulation, we are considering a real data simulation that is going to be happening in the WRF model. So for us, that means we're going to be doing a 3D forecast. We're not going to be doing a single column or 2D flow over a hill. There's going to be real input that goes into the preprocessor and into the WRF model. So meteorological data as opposed to idealized initialization for the input meteorological fields. There's an expectation that there's going to be a full suite of physics that is utilized inside of the WRF model, and a number of those fields will be initialized correctly inside of the real program. So microphysics, surface conditions, and maybe even providing some boundary conditions for nudging. A real data case also is a case that is on a sphere. So this is a non-Cartesian, this is a projected domain. So the input would be Lambert conformal, a Mercator, polar stereographic, or possibly a rotated lat-long grid. You can do global domains, but nowadays most of that is going to be absorbed by the impasse model. There's an expectation that the static fields are realistic. So we don't have smooth topography or idealized land use or no vegetation. We have information that comes from static data sets that are input to GeoGrid, and those get forwarded on all the way into the real program and then into the model. The lateral boundary conditions are time dependent. We don't assume that they are constant / fixed. We also don't assume that they are periodic or other idealized ways. The real program does have to generate a number of diagnostics. For example, what traditionally comes out of the WPS MetGrid program is temperature and relative humidity, geopotential height. None of those fields are what the WRF model would like to see. There's a requirement that initial fields are adjusted to be consistent. So, for example, you can imagine if you bring in data from multiple sources, they may not all agree that a particular grid cell is a water point or a land point. That's something that's fairly easy to figure out inside of the real program, and the WRF model does a poor job at adjusting to inconsistent values. It probably just segfaults. There is a computation of a base state field, so a separation into this reference and perturbation, and we'll talk about that in just a bit. Each of the model initialization times requires a full 3D volume of data. So there is an initial state that is provided for the WRF model. Because of the requirement for a time-dependent lateral boundary, there is a lateral boundary file that is generated for the course grid only. And finally, there is some vertical interpolation that goes on for the 3D meteorological fields, also for the soil data. You'll hear a number of presenters talk about the difference between runtime options and compile time options. It's kind of just a set of terms that you have to start being familiar with. When we refer to runtime options inside of the WRF modeling system, including WPS, what we are referring to are the options that can be used to change the simulation that do not require the code to be recompiled. And these traditionally come in via input files. What we choose is to use Fortran namelist files. Inside of the real program and WRF, it's called namelist.input. And for WPS, it's namelist.wps. These runtime options are different than what we refer to as compile time options. Based on the name, the compile time options are changes that are made to the source code that require the code to be recompiled before they can be activated. So these are modifications to the source code. They are changes to the compiler flags, for example, changing it from fully optimized to unoptimized, adding in CPP ifdefs, or modifications to the registry file. This last piece will also have a full talk on it, and it's how the WRF model allows users to make changes inside the source code without having to know too much about the whole modeling system. The standard input variables that come into the real program are entirely provided by the WPS program MechGrid. The MechGrid program handles the horizontal interpolation of meteorological fields and places that data into a file that the real program reads. All of the data transfer in the WRF modeling system is handled via files. The real program is able to accept any of the traditional vertical coordinates that come out of the MechGrid program. If the data is isobaric, or if it is on a terrain following sigma coordinate, or if it is a hybrid of both an isobaric and a sigma coordinate. The only requirement, and this is a strict requirement, is that the vertical coordinate is monotonic in pressure. It can either be increasing or decreasing. The fields that go into the real program that come from WPS are broken into mandatory and optional fields. This data comes from either the GeoGrid program, such as static data, topography, land categories, etc., or it's meteorological information, and it came from the decoded GRIBD data from UNGRIB. The mandatory data includes fields that you would expect: the 3D and surface information from horizontal winds, temperature, some sort of moisture, and the height field. While it's mandatory that a 3D soil moisture or 3D soil temperature is required, and it's only optional that a 3D soil moisture would be available, most of the land surface models require soil moisture. So for most modern land surface models, soil moisture is also mandatory. Traditional 2D fields that you would also expect to have as input for the real program provided by WPS would be fields such as surface pressure, sea level pressure, and landmass. A number of additional 2D fields are optional, but most of the national centers provide these in their GRIB datasets. The topography, sea surface temperature, sea ice flags, skin temperature, etc. Most users do not have to worry about the specifics of the vertical coordinate of the input data that's being provided by WPS, nor do they have to worry about the specific fields that are being provided from WPS. There are a number of known data sources that the UNGRID program has vtables to interpret. These vtables are associated with specific national center data sets that the WRF model understands and knows about. The vtable is able to pull out the necessary information from the GRIB files and provide that information into the MECRID program, and that's moved along into the REAL program for the vertical interpolation and diagnostics. As was mentioned, there is a separation into a perturbation and a reference state, a base state, for a number of time-independent, dynamically important meteorological fields inside of the WRF model. These base state fields are functions only of the topography and a few user-selectable constants, such as the model top, lapse rates, temperature at sea level in the middle of the domain. So anytime the topography changes, the base state is going to be modified also. This is entirely internal to the REAL program and the WRF model. The user, other than specifying these handful of constants, doesn't have to be bothered with the construction of the base state or the perturbation state. When there is feedback turned on for nesting, there is a mandatory consistency between topography on the course grid and various coincident points on the nest. Therefore, feedback requires the base state to be modified from the REAL program and the WRF model for every one of the nests. Because the base state is only required for the computational vertical coordinate that's utilized in the WRF model, only the REAL program and only the WRF model have to deal with the base state. No programs prior to the REAL program, no programs from WPS are concerned at all with the base state. The WRF model, and therefore the REAL program, both support a hybrid vertical coordinate. The hybrid vertical coordinate is such that it is a terrain following vertical coordinate near the surface, so where there is topography, the coordinate surfaces move up and down with the topography. And then it relaxes towards an isobaric surface aloft. The user is allowed to specify what that surface is. Traditionally, around 200 millibars is sufficient. This vertical coordinate is optional, and the user may choose to have only a terrain following vertical coordinate. However, since version 4, the default has been to fully exercise the hybrid vertical coordinate. The terrain following vertical coordinate, if we look at the eta levels where eta is equal to 0 is the model lid and eta equals 1 is the surface level, you can see the artificial impact of the coordinate surface even very high in the atmosphere. The solution, of course, is to have an isobaric field. The problem is that you run into the difficulty of the coordinate surface intersecting with the topography. The standard solution is to have a hybrid coordinate system where near the surface it is a terrain following vertical coordinate, but it quickly relaxes to an isobaric surface aloft. And then from that isobaric surface all the way up to the model lid, the vertical or the coordinate surfaces are flat isobaric surfaces. The potential temperature field inside of the WRF model is not strictly a dry potential temperature. Since version 4, the default has been to use a moist potential temperature. Users have to be a little bit careful when they're interpreting the data that comes out of the WRF model or the real program. The variable T is the dry potential temperature with a 300 Kelvin offset removed. So, for example, if the field was 300 Kelvin, the T field would report the value of 0. So it's easy to be confused and think that the field that's coming out is either a temperature in degrees C or some other unusual diagnostic. The T field coming out of the real program, coming out of the WRF model, is dry potential temperature minus 300. Inside of the model, moist potential temperature is used for all of the thermodynamic computations. It's been found in a number of high-resolution cases that the moist potential temperature gives a better solution. On the left, there are some artifacts of a moist field that are missing on the right. And those artifacts are caused by a strong vertical moisture gradient. So lots of moisture, for example, in the boundary layer and dry above the boundary layer. And then strong shear right at the top of the boundary layer. The entire WRF modeling system sends information along to the next standalone program via data files. So the real program, the real.exe program, accepts data from WPS, from the MECRID program. That information is modified, vertically interpolated, some diagnostics are computed, and then files are generated for use in the WRF model. For regional forecasts, the real program generates two files, the WRF input and the WRF boundary file. The WRF input file is an initial condition, and it's a single time period of a 3D volume of the entire state of the atmosphere for when the WRF model is starting. Wind, temperature, moisture, pressure, all the surface layer fields, all of the soil fields, the projection information, latitude, longitude, etc. There's a boundary file, the WRF BDY file. The WRF boundary file is constructed only for the most coarse grid. The lateral boundary conditions, the time-dependent boundary conditions for the nests, for the inner domains, are provided during the run of the WRF model by the parent domain. The initial condition file is the same format as is used as input to the WRF data assimilation, WRF DA code. This is referred to as a cold start, where you bring in information and update it with observations. For the lateral boundary condition, if we process in time periods of ungrid data and in time periods of MECRID data, then when we process n time periods of that data in the real program, the lateral boundary file contains only n minus 1 time slices. This is because of the way that we construct our lateral boundary conditions. So for example, if we have a 36-hour simulation that we're interested in, and the data is every 6 hours, we have 7 time period slices, but we have 6 boundary condition tendency steps. We know the value at time 0, hour 0, time slice number 1, and then we know the value at time period hour 6, time period time slice number 2. The difference of those two allows us to compute a tendency that is valid between hour 0 and hour 6. The tendency between hour 6 and 12 allows us to compute a tendency that's valid between hours 6 and 12. Likewise, all the way up to the end, the data at hour 30 and the data at hour 36 allow us to compute a tendency between 30 and 36. So we only end up with n minus 1 time periods of boundary data compared to the time periods that were processed inside of ungrib, metgrid, and the real program. What the boundary conditions look like is very similar to what happens inside of a nested run within the WRF model. In the region depicted as yellow, there is a single specified row and column that comes entirely from large-scale data. The information in this row and column comes from horizontally interpolated data from metgrid that was vertically interpolated inside of the real program and then was differenced inside of the real program to generate an initial value and tendency term. The next few rows and columns, depicted here as blue, are relaxation zones. The relaxation rows and columns allow both the large-scale terms from the ungrib, metgrid dataset to be averaged, to be nudged by the modeling system data that's coming entirely from the dynamics and physics inside of the WRF model. So a pure forecast region in this domain would be in the green area. A relaxation zone between the simulation that's going on and the large-scale forcing from the National Center model is depicted in blue, and the specified zone, which is strictly from the large-scale data, is depicted in yellow. The user can specify how wide the relaxation zone is. The default is about 5. Larger simulations or longer-term simulations use values that are 2 to 3 times larger than that. Linear or exponential decay of those relaxation zones is also possible. Excluding diagnostics, almost the entirety of the computational resources that are used inside of the real program is used to perform vertical interpolation. There are a number of vertical interpolation options that the user has available to them. And the important thing is, these options can have a significant impact on what the initial conditions and boundary conditions look like that are passed into the model. There's a subsequent lecture talking about how the registry is used. That registry talk describes how options that are unavailable in the standard name list are able to be added into the namelist.input file to modify the default way that vertical interpolations are handled. On the left-hand side is a picture of most of Colorado and a little bit of Kansas, Nebraska. The field that's depicted is topography. The area on the left, where it's kind of chopped up, is where the Rocky Mountains are located. And then the blue area, from about the third of the way over from the left all the way out to the across Kansas, is relatively flat, even though it's elevated topography. It's fairly smooth. The blue star identifies where Boulder is located. What we're going to do is show, with a few different options, the impact of the difference of activating an option versus not activating an option over this domain. For the next few slides, the left-hand side will always refer to the potential temperature field, and the right-hand side will also always refer to the U component of the horizontal speed. So the first option is this force surface in V-interp is equal to 0. What this says is we can optionally choose to force to have the surface utilized as part of the vertical interpolation if the data came in as isobaric. There are locations where the nearest sigma surface would be trapped by the pressure surfaces as opposed to one of the input surface that came in from the isobaric data. If we turn the option force surface in V-interp is equal to 0, which is not the default, the difference between the potential temperature field at the surface and the U field at the surface is mostly impacted over areas of strong topography. And that's a feature, that's an artifact that we're going to see in all of these options. When we have fairly smooth isobaric surfaces, such as the eastern 2/3 of the domain, the impact is very small with most of these vertical interpolation options. We can also say, not only are we requiring that the surface be used in the vertical interpolation, but that surface that is available from MetGrid is used as the bottom boundary condition for the first in levels, and in this case 6. So at level number 4, you can see on both the potential temperature and the U field, very smooth transition in the eastern 2/3 of the domain with the impact. However, once you get into the topography, there's very small scale noise that's introduced because of the change in the way that this particular surface field is utilized. We can adjust the order of the vertical interpolation. We can make it linear or second order. In this case, where you would see the strongest difference in that would be up towards the model top at the tropopause, or maybe 2/3 of the way up to the model top. And that's where this particular field is showing you. So at the tropopause, even in areas of topography, you can get significant small scale changes that are caused by the selecting a higher order vertical interpolation. You can choose to have the input data for the WRF model, sigma equals 1, defined entirely as the lowest level of input data that comes in from the large scale model. Typically, the WRF models run at much higher resolution, so this tends to have no real impact over relatively flat topography, which you see on the eastern 2/3 of the domain. But in areas of topography, this causes a substantial difference in the fields. Other options, you can optionally choose to smooth the outermost few rows and columns, this CG topo smooth. What that provides is an easier transition through the boundary region where the large scale fields are trying to adjust to the WRF model. And if those large scale fields are much coarser, it's reasonable to smooth them as we transition into the middle of the WRF domain. Perhaps used only for much older data where there was some sort of reason to suspect the validity of the surface. You can turn the surface fields off entirely that come in from the MechGrid package, and use surface equals to false. Again, on the eastern part of the domain, the fields are fairly smooth, but there is a strong discontinuity as we transit from one isobaric field to the next isobaric field when we're doing our interpolation, our linear interpolations. And then inside of the region which is dominated by high resolution topography or very noisy topography, we see very small scale features that are present, which would generate a lot of noise. So the purpose of showing these few slides for the vertical interpolation is to let the users know that there are a number of options that are available to allow you to fine-tune the initial conditions and the boundary conditions that are going into the WRF model. We've modified the name list and the associated registry to utilize a number of defaults that we think are reasonable. But since this is a research model, those options are entirely available for the user to go in and tinker with and adjust to get their fields just right. The internals of the vertical interpolation that go on inside of the real program are largely outside the purview of an individual user. The functions that go on basically are things such as the data is input and then it is vertically ordered. And vertically ordered means that there's a check to make sure that the data is monotonically increasing or decreasing in pressure. And then when we do the vertical interpolation, a column is either flipped or not to make sure that it's in a decreasing order when we go into the interpolation routine. Because the fields inside of the WRF model are the eta surfaces are a function of normalized pressure, all of the vertical interpolations inside of the real program are done in pressure space. So to compute the interpolation for pressure, we need to be able to compute what the surface pressure is going to be in the WRF model. So we have input temperature, topography, and height and moisture, and we use those to compute a surface field of what surface pressure field for the WRF model. We are given a vertical coordinate, and that's the normalized column pressure. We've seen it before where eta goes from 1 to 0. And that normalized vertical coordinate defines then the locations at each ij grid point where we are going to be interpolating to from our MechGrid data. The eta surfaces can be computed from the real program, or they can be entirely provided by the user. And that needs a little bit of a caveat there. Users have to be careful about that. It's probably best for new users to allow the real program to compute a reasonable set of eta surfaces for you. Traditionally, what we recommend is that users provide the number of vertical levels that they are interested in, and then let the real program compute a reasonable distribution of those eta surfaces given that total number. However, if a user would like to provide their own surfaces, there are some guidelines that should be adhered to. The surfaces should probably be less than about 1 kilometer in the free atmosphere. It's certainly okay to have fairly narrow, fairly thin layers near the surface. If you're choosing eta surfaces, for example, and you are someone who is interested in wind energy, it is not sufficient to simply go up 1 kilometer or so and say that that's the entire depth of the atmosphere. It's really best to go up to about 50 hectopascals as a minimum model top. 20 hectopascals, 10 hectopascals are absolutely fine. So really, it is safest to not choose your own eta values. If you have a set of provided values that come from a previous publication, that's entirely acceptable. But trying to compute your own eta levels is not recommended because it tends to cause troubles. There are a few namelist options that are inside of the namelist.input file. These are the runtime options that we mentioned earlier. Inside of the domains namelist.record, there's this evert, which is the ending number of the vertical levels. This is the full levels inside of the model. So 50 vertical levels for, in this case, possibly up to 3 domains. P-top requested is the pressure at the top of the model. This is an isobaric surface. This value is in Pascal, so it's a 10 hectopascal model lid, 10 millibar top. There are a few constants that a user can provide. The temperature at the surface at the sea level for the model, actually 1,000 hectopascals. The temperature, the isothermal temperature that the model would not get colder than above the tropopause, and the stratospheric base state pressure. These are reasonable defaults that are inside of the WRF model. A user can provide their own set of eta levels. What is the concern is that there is not a uniformity of the layer thickness. On the left-hand side is what we would like to see. This is a cross-section of the difference or the thickness of the eta layers as we go from the surface up to the model lid. And they're all about the same color because they're all about the same thickness, between 700 and 800 meters, entirely reasonable above the boundary layer. On the right-hand side are levels that were linearly chosen by a user. And what you tend to see is a set of levels that are finer in the mid-troposphere, and then they get an exaggerated stretch as you move from the tropopause up into the stratosphere. The problem with having very thick layers is that the absorbing layers at the top of the model require a certain thickness. And if the levels are several kilometers thick, you only have 1 or 2 levels that are inside that absorbing layer, and those absorbing layers are very ineffective. The take-home message is, unless you really know what you're doing, let the real program choose the eta surfaces for you. The real program and the WRF model utilize the exact same registry, which is a way that variables and fields are defined. They utilize the exact same build structure, and in many cases, the exact same source code is compiled into both executables. The real program and the WRF model are very tightly coupled together. There are a number of physical parameterization settings that are available inside of the namelist options that have initialization capabilities that are provided by the real program. So it is safest if you change physics options to rerun the real program. An easy example is for soil level interpolation. On the left-hand side at the bottom and on the right-hand side at the bottom, we have the two traditional input fields that are available from the U.S. Weather Service when we're picking up soil level data from the NOAA scheme and from the RUC scheme. The NOAA scheme has data valid between 0 and 10 centimeters, so the midpoint is 5 centimeters. It has the second layer between 10 and 40, the midpoint is 25 centimeters. The third layer is between 40 and 100 centimeters with a midpoint at 70 centimeters. And the deepest layer is between 100 and 200 centimeters with a midpoint at 150 centimeters. The RUC scheme is defined at levels instead of layers. And the levels are 0, 5, 20, 40, 160, and 300 centimeters. So inside of the WRF model, when we choose a land surface model option, depending on the a priori known defined locations and thicknesses of that particular scheme, variables are interpolated between either the NOAA or the RUC, for example, input data. For surface scheme number 1, which is the thermal diffusion only, the thicknesses are defined as 1, 2, 4, 8, and 16 centimeters. So we would end up with data interpolated from input data from MetGrid to those 5 levels. If the choice that the user made was to use the NOAA surface scheme, land surface scheme, the levels defined there are 0 to 10, 10 to 40, 40 to 100, and then 100 to 200 centimeters. So again, 5 layers, but the locations are going to be different. If we opted to use a 6-layer RUC scheme, or if we opted to use a 2-layer PX scheme, what we end up with is not only differing levels in the input data, whether at NOAA or RUC, to interpolate the data to, we end up with different numbers of levels of data that we interpolated to. The WRF model allocates space based on the number of levels that are defined or suggested because of the land surface model option. So, in recap, the real program and the WRF model are tightly coupled together because the data in one that gets passed to the other, there's an assumed mandate that that data is the exact same size in the other program. Physical parameterization schemes, and there are quite a number of them, are initialized by the real program, whether via the values that are provided or the actual dimensionality of the field. So the safe thing is, if you change physics options inside the WRF model, it is always safest to rerun the real program again. The real program takes hardly any time at all to run through a few time periods. So it's never going to cause you troubles to make sure that the physics options are identical in the real program with what you are running in the WRF model. If you are changing dynamics options, it's hardly ever required for you to rerun the real program. The entire purpose for the real program is to take meteorological data that is on the native coordinate from the first guessed model that came in from UNGRIB and went into MetGrid, and then vertically interpolate that data, compute some diagnostics, and pass data files on into the WRF model. The entire function of the real program is to move data from WPS to the WRF model. The data that comes into the real program are traditional meteorological variables that one would expect. Wind, temperature, moisture, pressure, the geopotential height at the surface and at various levels up through the top of the atmosphere as defined by the model are all required. Additional other variables are required too, such as the topography, the sea level pressure, surface pressure, and there are optional variables. But the line between optional and required is really not all that important. Most of the fields that the WRF model would like to see from large established national center models are all available inside of their GRIB datasets. And the UNGRIB program with the vtables that are already set up is able to pull the variables that the WRF model would like to see from those files and put those fields in the data stream that moves through MetGrid and then through REAL into the WRF model. The data comes ultimately from the national center, but it gets horizontally interpolated inside of MetGrid. It gets vertically interpolated and diagnosed inside of the REAL program. The only restriction that is on the vertical coordinate that comes from MetGrid is that the data is strictly monotonically increasing or strictly monotonically decreasing when it comes to pressure. There is a base state that is defined inside of the WRF model. What the base state does is provides a numerical contrivance, an engineering solution to allow the model to have a free extra digit or two when it's doing some horizontal differencing. So what we remove is a large portion of a value that we are differencing. And when we remove a nearly constant value from neighboring grid cells, we end up with a perturbation. And that perturbation is able to get a bit more resolution. The REAL program and the WRF model use the exact same base state. And that base state, those constants that are used in the base state, are also used to define the vertical coordinate. The other important thing to remember when you're playing around with the base state, there is no perturbation from the potential temperature that is on each level, but there is a constant offset for the entire 3D volume of data. When you see the variable T in the model output, it is the dry potential temperature minus 300 Kelvin. Just as there are input variables, there are output fields that are required. There are two output files. The first output file is the WRF input file. That's the 3D volume of data for an initial condition for the WRF model. There possibly could be one of these initial condition files for each of the required domains that the WRF model is running. The second mandatory file is the WRF boundary file. The WRF boundary file is only required for domain number 1, the most coarse grid. There are a large number of vertical coordinate options inside of the real program. Those are defined inside the registry, and the user may put those inside of the namelist.input file. However, what are the recommendations? It's simple. Initially, just try to use what the defaults are. If you see difficulties or problems in your initial data, then it's worthwhile to go back and take a look at some of the vertical interpolation options and see if you can tinker with those to get your initial conditions just exactly how you want. While this is called soil level interpolation, it's really a good example of why what we need to do is make sure that the physics options between the real program and the WRF model are consistent. There are a number of initializations that go on inside of the real program that provide data to the WRF model, and that data never gets into the WRF model that was used as a precursor for those fields. So the real program is the last time that we see isobaric data or the original input data for soil level information. So if we change physics options in the WRF model between what was defined in the real program, it's always safest to go back, rerun the real program with the physics options that are going to be used inside the WRF model, and then use those exact same physics options inside of the WRF model. If there are any questions about this presentation or any of the other presentations in the rest of the WRF modeling system tutorial, please go ahead and send those to the WRF forum. There's a general statement for the WRF user support that is provided, and there are a number of resources that a user can take advantage of. WRF has a nice homepage that details not only information and documentation, but also schedules and availability of tutorials and workshops. Finally, the WRF and WPS source codes are maintained with an open development capability on GitHub at the following locations. And that's the end of this presentation.